Welcome back. In topic 2, part 1, we try to explain the mass and momentum governing equations. In topic 2, part 2, we will interpret energy equation. 1. First law of energy conservation statement. During a heat transfer process, energy can cross the system boundary in and out, and the energy can be generated within the system. Therefore, the change in energy content of our system is equal to energy input minus energy output plus energy generated. But the question is, what kind of energy can cross the system boundary? Because there are so many different energy forms. For convection, the answer is that. First, the fluid is in motion, therefore the mass flow rate can carry the energy in and out of the system. Second, the viscous force can do deformation work to push the energy in and out of the system. Third, through direct contact, the molecules can carry the energy in and out of a system. Therefore, based upon the energy carrying mechanism, the first law statement in equation 3.1 can be restated in equation 3.2, which is energy in and out of the system carried by mass flow, viscous force, and molecules, plus the energy generated is the cause of the energy change within the system. 3. Now you may be ready to interpret energy governing equation 3.3 after it is multiplied by the differential control volume dV with the viscous dissipation phi defined in equation 3.4. If you wonder what is viscous dissipation, we'll discuss this later in detail. First, if we compare first law statement in equation 3.2 with the energy governing equation 3.3, we discovered that this is the energy stored inside the control volume in the form of enthalpy. This is energy generated within the control volume at a rate of Q triple prime. This term represents all the conduction heat into the control volume minus all the conduction heat rate leaving the control volume. Then this term is the viscous work, and this term represents the energy in and out of the system carried by the mass flow. Second, with the proper training on the derivation of a conduction heat equation, the physical meaning for these three terms is getting more clear and more obvious. At least I hope so. On the other hand, for these two terms, it is hard to make immediate connection with its physical meanings. Therefore, next, we will elaborate on these two terms in terms of its physical meaning. 4. We will demonstrate that the convection term in the energy governing equation represents the energy in and out of a system carried by the mass flow. This is our differential control volume dx dy dv with enthalpy rate along the boundary. First, we define enthalpy H and list mass conservation, which is a continuity equation. Second, we check this term in the bracket and label it term 1 by adding 0. Term 1 plus temperature times 0, still 0. Next, we combine the first term and the third term and then apply product rule to get the new first term. Similarly, we combine the second term and the fourth term and then apply product rule to get the second new term. We label this term 2. Now, term 1 can be represented by term 2. Third, for this convection term, we replace term 1 with term 2. Next, we take the constant density and the specific heat and differential size dy dz into the first derivative, combining density, extraction velocity, and surface area dAx gives mass flow rate in the x direction. Combining specific heat and temperature gives enthalpy. Similarly, if we take rho Cp and dx dz into the second derivative, combining these parameters gives mass flow rate in the y direction. Combining these two variables gives enthalpy. Finally, we will apply Taylor-Series expansion approximation to the first term and second term to get the enthalpy rate in the x direction and enthalpy rate in the y direction. Now we demonstrate that the convection term has the physical meaning, which is mass flow carries enthalpy over particles entering and leaving the control volume. 5. We will derive the viscous work to help you understand the viscous dissipation term and make connection with this mathematical expression. First, what is viscous dissipation? It is defined as an irreversible process when the work done by the viscous force on the fluid is transformed into heat. For example, we have a 2-plate in between is a fluid like honey. If you push the upper plate, you feel the resistance from the honey. This resistance is our viscous force. Due to the relative motion between the fluid layer and the upper plate, we have friction, and friction will generate heat. Therefore, we call this process is viscous dissipation process, because friction generates heat, and the heat is dissipated into the fluid we stated. The reason that it is viscous work or deformation work is that the viscous force times the fluid velocity happens to be the work rate. Second, therefore, viscosity times the viscous dissipation phi times the differential control volume dV represents the rate of viscous dissipation in a unit of a watt. In a plain words, it represents how fast or slow the heat is generated within the fluid due to the friction. Third, however, viscous heat generation is significant only when the velocity gradient is large. But we wonder how large is large. We will use spacecraft entering into the atmosphere as an example. We assume the viscosity of air is mu with a small value, the speed of a spacecraft u with a very large value. Assume the boundary layer on the surface of the spacecraft that y is small, then the velocity gradient that u over dy has a big value. Finally, the viscous dissipation rate per unit of volume is viscosity mu times the velocity gradient square. So the value is large. Generally speaking, in engineering application, if the velocity gradient is small, say less than 1,000, the dissipation term tend to be neglected. Fourth, we will use example 3 to demonstrate the deformation work done by the viscous force is represented by equation 3.8. This is a viscous tensor. In two-dimensional flow, it has 4 components. And this is our differential control volume, dx, dy, dv, with a deformation work along the boundary. A. Work rate done by extraction viscous force, which is the sum of extraction viscous force times extraction velocity. It is represented by normal viscous force times velocity at x location plus normal viscous force times velocity at x plus dx location plus shear viscous force times velocity at y location plus shear viscous force times velocity at y plus dy location. Next, we apply Taylor expansion approximation to temperature difference in the y direction and the temperature difference in the y direction to get force times the velocity gradient, force times velocity gradient. Next, we simply replace Txx with its definition, Tyx with its definition. Finally, we do the mathematical multiplication to get term 1, which is half of the equation 3.8. B. Work rate done by y direction viscous force, which is sum of y direction force times y direction velocity. By following the same steps, we get term 2. Which is the sum of the viscous forces times the y direction velocity. C. The work done by all the viscous force in both x direction and y direction is viscous forces. It's represented by combined the term 1 and term 2. With the proper mathematical rearrangement, we will get term 3, which is exactly the equation 3.8. Therefore, the viscous term represents the energy in and out carried by the viscous force through the deformation work. At this point, we covered topic 2, part 2, interpret energy governing equation. The quick summary for the physical meaning for the energy equation is energy stored, energy generated, energy in and out of system carried by molecules. So the mechanism is a diffusion. Energy in and out carried by the viscous. It represents the heat generated by friction. Therefore, it is a friction-induced heat generation mechanism. Finally, this represents the energy in and out carried by mass flow. This is the convection mechanism because the velocity carried the temperature gradient to move around. Remember, when the velocity carried the velocity gradient move around, it is acceleration. Okay, see you next time. Have fun.